The title of my talk is Deep Learning Quantum States for Hamiltonian Predictions. These are my collaborators on this work, Shi-Ju Ran and Professor Zhangchun Tu from Beijing Normal University. Our paper can be found on arXiv. Well, quantum many-body systems can be very interesting because it may lead to fruitful novel phenomenon. Just allow me to take one of our own work as an example, where we simulated the spin-1 and ferromagnetic Heisenberg sawtooth chain by density matrix renormalization group algorithm. In this model, we found a very fruitful ground state phase diagram as shown in this figure. Where the magnetic field is very small, you can see that the whole system is in the Hurdan phase. By taking the coupling constant in this region, if you increase the magnetic field, the system will firstly get out of the Hurdan phase and enter a topologically trivial phase. If you continue increasing the magnetic field, the system will re-enter a partial Hurdan phase, where the spins in the sublattice A will form the Hurdan state, and this will lead to the non-trivial topological degeneracy in the entanglement spectrum. Okay. Simulating quantum many-body system is in general very challenging. For the conventional methods such as mean field, perturbation theories, these methods can work well for the regions that are far away from the critical point. But within the critical region, near the critical point, this method may fail due to the strong correlations of the system. Well, you can use some more advanced numerical methods such as quantum Monte Carlo, density matrix renormalization group, or tensor network methods. With this method, you can simulate the physics far away from the critical point with high accuracy and efficiency, but still near the critical region in the vicinity, due to the non-correlations and large entanglement, this method may still be inefficient or inaccurate. So an interesting question arises. Can we learn the states far away from the critical point and use the states to train a machine learning model and use this model to access some information in the critical vicinity? This is also one of the main motivation of our work. Well, at hand, the most promising machine learning model is neural network. It has achieved great success in machine learning. One famous example is playing Go game, which is deemed as one of the most difficult game for computers. But for just self-training for just a couple of days, machine learning neural network can beat most of the human experts. This is really very impressive. Well, neural network has also been applied to solve physical problems in a data-driven way. This is one example of work from Yale. They propose to use neural network to predict the potential term in the Schrödinger equation by giving some ground states or excited states. They take the harmonic oscillators and the hydrogens as example to show the validity of their proposal. In this talk, I will introduce our recent work on using machine learning model to predict the parameters of many-body Hamiltonians given some ground states. Consider a Hamiltonian parameterized by a parameter alpha. This alpha can be coupling constant or magnetic field. So our main target is to predict the alpha given the ground state phi alpha. The main steps of our proposal is as follows. Firstly, we have ground states phi alpha or its local reduced density matrix. To do the prediction, we firstly map this density matrices or state into images by a technique known as the Qubism map, which I will introduce later. Then we use a deep convolutional neural network to map this image into the prediction of our target parameter alpha. So in this way, we can predict the parameter of alpha given the ground state. So this is an inverse problem by giving the ground state by solving the parameter of the Hamiltonian given the ground state. Well, the machine learning model we choose is convolutional neural network, which is one of the most powerful machine learning model for processing images. as the deep learning methods develop, you can see that the error for processing real-life images with CNN decreases fast as the complexity and the depth of the neural network grows. Well, another key ingredient of our proposal is called Qubism, which is a map from quantum states to images. This is proposed by a Spanish group. In this figure, you can see that some color pixels which correspond to the non-zero coefficient of the quantum state. You can see that in general, this non-zero coefficients or the colored pixels form some patterns of fractals, which will reflect certain physical properties of the quantum state. Here we show that we show the images from the ground states of the models that considered in our work, which are quantum Ising model and XY model and XY model. You can see that for different parameters in the Hamiltonian, such as the magnetic field or the coupling constant of the SC term, you can see that the pattern actually indeed change with this parameter, but it is unlikely that a human being can learn the relations between this parameter and the patterns by eyes. It is almost unlikely. So we propose to use the convolutional neural network to learn the relations. However, one drawback of Qubism map is that the pixels in the image have one-to-one correspondence to the coefficients of the quantum state, whose number will increase exponentially with the system size. What we propose is that we can learn from the local reduced density matrix of a finite size bulk. Normally, we take the size of the bulk LB equals to 8, and the total system size equals to 64. Well, in detail, we firstly have the ground state, then we calculate the reduced density matrix of this bulk and do the purification to map the density matrix to a pure state. Then we use the Qubism map to map the pure state into an image. Then this image will be fed to the CNN, and then the CNN will tell us the value of the parameters in the Hamiltonian. This figure shows the performance of our model. For each point in this figure, it represents one quantum state. The x-axis of this point of each point is gives the correct value of the parameter in the Hamiltonian, for example, the magnetic field or the coupling constant. The y-axis gives the prediction of this parameter. So if you see these points fall onto the dotted line, it means that the prediction is quite nice. We calculated the MSE error, the mean square error of the. To train the model, we need some training states to optimize the variational parameters of our machine learning model. What we do is we randomly select about 100 parameters from 0 to 1, and use these states, the ground states, to train the convolutional neural network. We take, in a similar way, we take another set of ground states as a testing set. The testing states will not be fed to the convolutional neural network to do optimization. It is only to test if the neural network can still accurately classify this kind of states. So you can see that for the testing error, it is still very small. It is about 10 to the minus 4. It means that our model can accurately predict the states that are not used in the optimization procedure. Particularly for the quantum Ising chain, there is a critical point at h equals 0.5. You can see that for the whole region, the prediction of the ground states of the quantum Ising chain is uniformly accurate. It means that the criticality seems to have low effects, or at least no negative effects on this prediction. We will come to this issue later. To test the generalization power of our model, we introduced the generalizing set, which is marked by the yellow area. Inside this area, we take no training states to optimize the machine learning model. It means that the machine learning model only learn from the states distributed in the blue region. In the yellow region, there will be no training states. But still, you can see that for this green or red line, they can still well predict the parameter of the states inside this generalizing set. Here, there's a very strange shape of this prediction curve. Like here, we take this whole system size as a small number, which equals to 16. In this case, the problem is that the system is gapped. It means that you have finite energy gap among the eigenstates of the Hamiltonian. It means that within each gap, if you change the parameter h or jz, the ground state will not change. It means that different values of jz or h correspond to the same ground state, which will definitely confuse the machine learning model because machine learning model prefers that different h or different jz correspond to different ground state. But if you have the finite gap, this will not be the case. So this will need to quite bite the performance of our model. By increasing the final system, the total system size to 64, you can see that the gaps will be largely suppressed, and the testing and the generalizing error will be largely ignored. Okay, and particularly for the quantum Ising model, you can see that this generalizing range is just contains a critical point. It means that the neural network only learns from the states that are far away from the critical region, but it still can predict the parameters of the ground states in the critical vicinity. So this is quite interesting observation. Our model can be applied to 2D systems. Here we choose a finite size square lattice. This figure shows the 1D path of how we do the DMRG simulation. And we choose the 8 spins in the middle of the system to calculate the reduced density matrix. This figure shows the images from the Qubism map from this reduced density matrix. You can see that there are more colored pixels in the image. It means that the reduced density matrix of the ground state of 2D system are much more dense than that of the 1D system. But still, we obtain similar accuracies on these 2D systems. You can see that the testing error and the generalizing error is still comparable to that of the 1D system. It means that our model can predict well the parameter in the 2D Hamiltonians. Well, this figure shows how the generalizing error changes with the system size. In the main figure, we fix the box size for the reduced density matrix as LB equals to 8. When we increase the total system size, you can see that the generalizing error decreases as expected. This is what we expected. Oh, sorry. In the inset, we fix the total system size L equals to 64, and we increase LB. Then we find that the generalizing error also decreases with LB, but it converges to LB equals 6 or 8. This means that you can see that in this figure, we choose the XY chain, which is actually gapless. So this is the 1D XY chain. It is actually gapless and possesses a long correlation length. It means that we do not need to take LB as large as the correlation length. In this case, the machine learning model still managed to predict the parameter of the given ground states accurately. This is not the same with the experience on the convolutional methods, because normally the prediction will be difficult, or the simulations will be difficult if the system is gapless or has non-range correlations. But here, if the correlation is none, you will not have the gap among the eigenstates. It means that you will not have have different values of parameters correspond to the same state to confuse the machine learning model. So this is different from the conventional physical approaches. This figure shows the generalizing error with different weights of the generalizing set. It means the delta means how wide we take the generalizing set. Delta is the weight of the yellow region in which we do not take any training samples. Surely, if you increase the width of the generalizing set, it will become more difficult for the machine learning model to predict the parameters inside the generalizing states. However, even if we take the delta equals to 0.8, it means that the training regions are very narrow. It is only from 0 to 0.1 and from 0.9 to 1. So the training states are taken in very narrow regions. Still, the generalizing error is not big. It's just 0.05. The MSE of the predictions of the generalizing states. This means that our model has superior generalizing power for these prediction tasks. Okay, in this figure, we compare the 1D CNN with the 2D CNN because, we use the Qubism map to map the quantum state into 2D images. Then we use the CNN to process this image, but we can use the 1D CNN where we just reshape the quantum states, the coefficients of the quantum state into 1D vectors. So without Qubism map and the 2D and by using 1D CNN, you can see similar performance for the performance for the testing range, but for the generalizing range, for the generalizing states, 2D CNN is much more better than 1D CNN. This benefits from both the Qubism map and the superior power of 2D CNN for processing the 2D images. In summary, we propose QubismNet to predict the parameters of quantum many-body Hamiltonians given its ground states. Firstly, we map the ground state or its local reduced density matrix into images by the Qubism map. Then we use CNN to transform the images into the predictions of the parameters that we are interested in. We benchmark our models on several lattice systems, such as the XX model, XY model, and the quantum instinct model on 1D and 2D lattices. Our results show excellent training, testing, and generalizing powers of our model. Actually, our work implies that we can learn from the states that are easy to access, and train the machine learning models to access the information inside the regions that are not easy to access. So this is more or less like a shortcut to access the information in a difficult region. It would be interesting to ask what kind of information can be accessed by following these shortcuts with the help of machine learning. Another interesting thing is that if we can use TN instead of neural network as the machine learning model to deal with the problems of quantum physics. But still, TN is a very young quantum-inspired machine learning model. There still exists a huge gap of performance for machine learning tasks between tensor network and the neural network. But we believe that tensor network can provide a more general mathematical form for machine learning compared with neural network. For instance, we make some efforts to develop a nonlinear tensor network model and achieve quite nice accuracy. Even this accuracy is still lower than the accuracy of the state-of-the-art neural network, such as ResNet. But the gap between the tensor and the neural networks are closing. We believe that eventually in the future, tensor network can be a powerful machine learning model, particularly to deal with the quantum physics problems. Thank you very much for your attention.